So as we have seen in the previous video about the development of the quantum mechanics, which was this theory was given by Erwin Schrödinger, and he developed a mathematical treatment or expression or equation that explain both the wave and particle nature of the matter, and that theory is known as quantum mechanics. So what was that mathematical expression? It's a very detailed equation derivation, but we need not to memorize that equation. So according to Schrödinger quantum mechanics, he gave this a wave function which is this kind of very lengthy and long mathematical expression or equation. What it says, basically it expresses the probability and or density or electron density in the 3D space, and after solving this equation we get the quantum numbers. So, and there are 4 quantum numbers related to every atom of element, and they are called principal quantum number, orbital quantum number, this is also called angular quantum number, magnetic quantum number, and spin quantum number. And these are the function that are capital R, small r, and then theta, and all the other mathematical sign, they represent these quantum numbers. And in a simple way we can understand that principal quantum number is assigned as a small n, which start from 1 to 3, and angular or orbital quantum number start from small l, which is equal to small n minus 1, means principal quantum number minus 1. So if n is 1, then l will be 0. If n is 2, then l will be 1, like that. And magnetic quantum number is represented by small m and l, and which is equal to minus L2 plus L. And spin quantum number is represented by ms, which is plus half and minus half. So let's see in detail about this quantum number, and this is the very important part of this chapter, which is quantum mechanics and quantum numbers. So when we solve this Schrödinger equation, wave equation, which gave the set of the wave function or orbitals and their corresponding energies, so it basically describes that where the electron will be located in an atom, and so mathematical expression will give you the exact location or probability of finding the electrons basically in the 3D space. For orbital, and each orbital describe a spatial distribution of electron density, so where the most probability of electron will be there, that area is called the orbital. And orbital is described by a set of 3 quantum numbers, which we have seen in a previous slide. Basically there are 4 quantum numbers. Principal quantum number, once again, orbital or angular quantum number, magnetic quantum number, and spin quantum number. So we will look at in detail about these quantum numbers once again. So first quantum number is principal quantum number, which is represented by small n. So the principal quantum number small n describe the energy level on which the orbital reside. So basically you can also compare that these orbitals or quantum numbers are exactly like a address of the electron, where the electron will reside, and the value of small n or any integer which is equal or more than 1. So small n would be like 1, 2, 3, 4, any integer, and these correspond to the values in the Bohr model. So because Bohr model was also gave some valuable information in supporting this quantum mechanics, and so basically small n is the energy level, or which is called quantum number, and you have to remember that small n is start from 1, 2, 3, 4. Next quantum number is angular momentum quantum number, which is represented by small l, and what is this? So angular quantum number defines the shape of the orbital. So allowed values for small l are integers ranging from 0 to n minus 1, and later design that different values of small l, this define the shape of the orbital. So for an example, small n is equal to 1. For small n is equal to 1, then small l, which is angular momentum or angular quantum number, will be small n minus 1, means it will be 0. If small n is equal to 2, then small l will be 2 minus 1, means it would be 1. So value of l will start from 0, 1, 2, 3, and later also used to describe the shape of the orbital. 0 is for s orbital, 1 is for p orbital, 2 is for d orbital, and 3 is for f orbital. So angular quantum moment number define the shape of the orbital, and there are four or type of orbitals are there, s, p, d, f, and we will look at those first. So s orbital could be 1s, 2s, 3s, and s orbital is always spherical in shape. So the value of small l for s orbital is 0, and they are spherical in shape. The radius of the sphere increases with the value of n. If small n is equal to 1, so small l will be 0, and the shape of the s orbital will be smaller compared to 2s and 3s. So and these angular momentum quantum number means small l describe the shape of the orbital, and small s orbital is spherical in shape. So let's see a little bit more about the s orbital. So for an ns orbital, the number of the peak is n, means suppose this is ns orbital, 1s orbital, so the number of peak will be number 1. For 2s, number of peak will be 2. So here it shows basically this picture shows 1s, 2s, 3s, and you can see this is the cross section, horizontal and longitudinal both, of the s orbital, that shows that there is some node, and then this graph goes at very high peak also. So for an ns orbital, the number of nodes where there is a 0 probability of finding the electron is n minus 1. So at this node the electron finding probability is 0, and the most of the electron probability will be in the high peak area. So this shows that s orbital has spherical in shape, and where the electron probability will be more in finding. compared to nodes and peaks. So and one more important thing is shown in this picture. You can see here, because of this is derived, all this derived from quantum mechanics Schrodinger mathematical expression. So if a small n is equal to 1, then L will be 0, means there is no node, and a small n is equal to 2, then small l will be 0, and this also shows for the number of s orbital. So L is 0 means always for s orbital, and 2 and 3 is for different energy levels. So we will see in the, as we will try to give the calculate the quantum numbers for every element. Next is the p-orbital. So p-orbital look like a dumbbell shape. So value for the p-orbital is always 1, and they have two lobes with the nodes between them, and they are called px, py, pz. So x p, sorry, this is a name as a pz, px, py. So you can say like a px, py, pz. So there are 3 p orbitals. They are arranged on x, y and z axis, and they are in dumbbell shape because they have two lobes, and the probability of finding of electron will be more on the lobes compared to the nodes. Third type of orbital is the d orbital, and d orbital, for the d orbital the value of L for the d orbital is 2, and the 4 of the 5 d orbitals have 4 lobes. The other resembles a p orbital with the donut around the center. So you can see the d orbitals are double dumbbell shape. They are called like dyz, dz, xz, dxy, and dx square, y square, and dx square. So these are the mathematical expression and derived from the Schrodinger wave mechanics equation that shows the d orbital. There are 5 d orbitals, and they are double lobes, and the last one is circular around like a donut shape. So and the fourth orbital is very complicated in the shape, not shown in the text, and there are 7 equivalent orbital in sub-level, and for f orbital L is equal to 3. So there will be 7 f orbital, like s orbital is 1, p orbitals are 3, and d orbitals are 5, and f orbitals are 7. F orbitals are there. So next is so far we have studied about the two quantum numbers, principal quantum number and angular momentum quantum number. So third one is magnetic quantum number. Magnetic quantum number describe the three-dimensional orientation of the orbitals, how the orbitals are oriented. Allowed values for small m, l are integer, and ranging from -L to L including 0. So for an example, if small n is equal to 0 for principal quantum number, then small l will be, sorry, small n will be 1, then small l will be -n-1, which is 0, and then small ml, which is magnetic quantum number, will be also 0. But for if n is equal to 2, then L will be 2 minus 1, which is 1, and then ml will be minus 1, 0 and plus 1. So like that, magnetic quantum number small ml will be equal to minus L2 plus L, means minus L is minus 1, 0 and plus 1. Therefore, for any given energy level, there can be 1 s orbital, 3 p orbital and 5 d orbital and 7 f orbitals will be there, and so forth. So and they represent for p orbitals, because px, py, pz, and if small n is equal to number 3, so small n will become 2, and then because 3 minus 1 is equal to 2, and then ml, which is magnetic quantum number, will become minus 2, minus 1, 0, plus 1 and plus 2. So they represent for d orbital, 5d orbital. So magnetic quantum number, once again, they are represented by small l, ml, and their values are from small minus l to plus l. Once again, about the magnetic quantum number, which is small ml, and orbitals where the same value of small n form an electron shell, and different orbital types within the shell or subshell. So here is the before reading this table, I would like to go for next slide, and then we'll go to that table. So last one is the fourth quantum number, is a spin quantum number, which is represented by small ms, and in 1920 it was discovered that two electrons in the same orbital do not have the exactly same energy. The spin of the electron describes the magnetic field which affect its energy, and this lead to the spin quantum number, which is new one, came very late after quantum mechanics. So the spin quantum number has only allowed values plus half and minus half. So if one orbital have two electrons, so one will move in the like clockwise and another will move to anti-clockwise, like that. So now we can summarize these quantum numbers. So this table shows that relationship among the values of small n, l, m through n4. So you can see if small n is equal to 1, then the possible value for small l, which is magnetic angular quantum number, will be n minus 1, which is 0, and then subshell, this represent for 1s, 0 is for s. So all zeros have s, and all 1 is equal to p, all 2 is equal to d, all 3 is equal to f. So we can write like 1 s, and then possible ml value will also be 0. So number of orbitals in the shell will be 1, this one, and total number of orbital in the shell will be 1. And if there is a small number, small n is 2, then the possible value of L will be 0 and 1, and then small ml, which is magnetic quantum number, will be for 2s will be 0, and then for this one, because it start from minus 1 to 0 plus L, minus L to plus L, so with 0, so 1 0 minus 1. You can also write like plus and minus 1 also first. So likewise you can read these also. 3 is if a small n is equal to 3 and if a small n is equal to 4, what will be the value of a small l and a small ml. So here this is the formula which give very valuable numbers. If we have to find out total number of orbital in a cell, which is n square, total number of orbital in subcell will be equal to n square, and total number of electrons in a cell is represented by 2n square. So you have to just multiply by these. So this was about the quantum numbers, and there is one more last slide for this one. So for a small n is equal to 1, L will be 0, M is equal to 0. Small n will be 2, then L will be 2 values 0 and 1. Small m will be 0, and for 1 m will be minus 1, 0 and plus 1. And for a small n 3, small l will be 3 orbitals will be there, 0, 1 and 2, and then orbital will have some subcell, that is 0 plus 1, 0 and minus 1, 0 and plus 1, and then these orbitals for the angular quantum number p. So this is the way we write the quantum numbers for the quantum mechanics theory, how any electron will be there, where the electron will be there, and how many, what would be the mathematical expression for that one.